Okay, so for today, we will continue Module 7. This is the last part of Module 7, all about the inverse Laplace transform and its application in solution of an initial value problem. If f of s represents the Laplace transform of a function f of t, that is, as we discussed last meeting, the Laplace of f of t is equal to f of s, we say that f of t is the inverse Laplace transform of f of s. And by definition, it is defined by the integral of this function. So the inverse Laplace transform of a function of s is equal to 1 over j times 2 times pi, the integral from 0 minus j infinity, to sigma minus j infinity to sigma plus j infinity. Those are the lower and the upper limits of f of s e to the st ds is equal to a function of t u of t, where u of t is equal to 1 when t is greater than or equal to 0 and 0 when t is less than 0 is the unit step function. So if you want to find the inverse Laplace of f of s, then you are to take this integral by definition. But in our class, again, I will not ask you to integrate, but we will be using the table of the inverse Laplace transform of some elementary function. If you recall in our last discussion, I presented to you the table of the Laplace transform of some elementary functions. So in finding f of s, you are given f of t. But this time, you are to find f of t given your f of s. So we are now to evaluate the inverse Laplace transform of f of s for us to find the function f of t. This table presents to us the inverse Laplace transform of some elementary functions. So we will be using this table as our reference in solving the inverse Laplace transform of f of s. So if you have f of s of 1 over s, then your function f of t is 1. If you have 1 over s minus a, then your f of t is e to the at. If you have s over s squared minus a squared, then the function is cosine of at. If you have n factorial over s to the n plus 1, the function is t to the n, and so on and so forth. Okay? So this is similar to what we had previously, but you are given of f of t, and in the second column, you are given of the Laplace transform f of s. Take note that in this table, you also have e to the at times t to the n, a to the at sine of omega t, cosine of omega t, and the two hyperbolic functions of sine and cosine with the product e to the at. Okay, so again, we are to refer to this table if we are to find the inverse Laplace transform. Because if we are going to use its definition, it will require us a series of integration. Find the inverse Laplace of 1 over s to the fifth. So what function can we relate this 1 over s to the fifth? It is somewhat related to our Laplace transform of t to the n. What is the Laplace transform of t to the n? That is equal to n factorial over s to the n plus 1. So if you are going to look at here, s to the fifth, which means that n is 4. Okay? So there should be 4 factorial in the numerator. So we multiply 4 factorial over 4 factorial to our function. So this would be equal to 1 over 4 factorial, the inverse Laplace of 4 factorial over s to the 4 plus 1. And therefore, this is equivalent to what is 4 factorial? 4 times 3 times 2 is 24. So 1 over 24. And what is now the inverse Laplace of 4 factorial over s to the 4 plus 1? That is simply equal to t to the 4. So that is 1 over 24 times t to the 4. And that is your function of t. Okay? Next problem. Find the inverse Laplace of 1 over s squared plus 9. So when we have s squared plus 9 in the denominator, it relates to sine and cosine. But when we have numerical value in the numerator, then it relates to sine. Because when you have cosine, it should be s in the numerator. So it should be sine. So let us write here what is the Laplace transform of sine of 80. That is equal to 1 over, or a over s squared plus a squared. But in the denominator, you have s squared plus 9. So it means that our a is 3. So the numerator should be 3, but you have here 1. So therefore, you are to multiply the given function by 3 over 3. So this would be simply equal to 1/3 the inverse Laplace transform of 3 over s squared plus 9. And again, the inverse Laplace of 3 over s squared plus 9 is sine of 3t. And that is the function of t. Okay? So this is problem 4 already. Problem number 4. Find the inverse of 6 minus 2s over s squared plus 4. So with this, we are also to apply the linearity property even if we have the inverse Laplace transform. Okay, so how are we going to find the inverse of 6 minus 2s over s squared plus 4? So this is equal to bilinearity property, that is the inverse Laplace transform of 6 over s squared plus 4 minus 2s over s squared plus 4. So you see here that there is s squared plus 4. So similar to our previous example, s squared plus 4 relates to sine or cosine, but the numerator is numerical value, so you are to relate it to sine. And it should be 2 in the numerator. So to make it 2, 6 is simply equal to 3 times 2. So this is equal to 3 times the inverse Laplace of 2 over s squared plus 4. That is the first term. And then, for the second term, you have s squared plus 4. Again, relating to sine or cosine, but the numerator is s, so this relates to cosine. So that would be minus 2, the inverse Laplace of s over s squared plus 4. And therefore, the inverse Laplace of 2 over s squared plus 4 is sine of 2t. And for this one, s over s squared plus 4 is cosine of 2t. So therefore, you have here 3 times sine of 2t minus 2 cosine of 2t. And this is your inverse Laplace transform of 6 minus 2s over s squared plus 4, or simply your f of t. Okay? So this is problem number 4. Now we go to initial value problems. So you need the knowledge of inverse Laplace transform for us to be able to solve initial value problems as applied to differential equations. So the Laplace transform ideally suited for solving linear initial value problems in which the differential equation has constant coefficient. Such a DE is simply a linear combination of terms y, y prime, y double prime up to y to the n. And the initial value problem, a sub n y to the n plus a n minus 1 y to the n minus 1 plus up to a sub 0 y1 is equal to g of t, subject to the given conditions. Y of 0 is y sub y at x equals 0 is y of 0, y prime of 0 is y1, up to y to the n minus 1 of 0 is equal to y n minus 1, where the coefficients and the initial values are constant, can be conveniently solved by the Laplace transform. By the linearity property, the Laplace transform of this linear combination is a linear combination of Laplace transform. So equation number 2 is the application of linearity property to equation number 1. So you take all the Laplace or the Laplace of all the given terms. Then we have, by applying the transform of derivatives, you will have this resulting equation where the Laplace of y of t is equal to y of s and Laplace of g of t is g of s. So in other words, the Laplace transform of a linear differential equation with constant coefficient becomes an algebraic equation in y of s. And we can write that in equation form, that y of s is equal to q of s over p of s plus g of s over p of s, where your p of s is a n s to the n plus a n minus 1 s to the n minus 1 plus up to a sub 0. And qs is a polynomial in s of degree n minus 1, and g of s is the Laplace transform of g of t. Typically, we put the two terms in equation number 3 over the least common denominator and then decompose the expression into two or more partial fractions. And finally, the solution of the original value problem is given by y of t, which is equal to the inverse Laplace transform of y of s. So you will see that procedure in the next examples that I will solve for this topic, initial value problems. Okay, so let us continue for us to see what this y of s, q of s, g of s, p of s are, and what is this y of t, which is the solution of our initial value problem. So we are actually to find y of t, which means that it will involve finding the inverse Laplace transform, since we are actually finding your y of t or your f of t. Okay, So we just use here y of t because you have here y of s. If it is f of s, then you are to find f of t. If you have g of s, then you have g of t. Okay, let us have this example problem. Solve y double prime of t minus 4y prime plus 4y of t is equal to 4e to the 2t. This is again function of t. Given conditions that y of 0 is equal to negative 1 and y prime of 0 is equal to negative 4. So in our solution, it will always involve partial fractions. The reason why I asked you last time to recall or to study partial fractions if in case you forgot how to solve partial fractions. Okay? So let us have the solution for this differential equation using Laplace transform and its inverse. So what do we need here is the transform of derivatives. If you can recall, you have here the second derivative, then the first derivative. Okay? So taking the Laplace of all terms of the given differential equation, you have here the Laplace of y double prime of t minus 4 and applying also linearity property minus 4 times the Laplace of y prime of t plus 4 times the Laplace of y of t is equal to 4 the Laplace of e to the 2t. Okay? So we determine first the Laplace of the second derivative. So if we recall, that would be equal to what? That is equal to s squared f of s minus s f of 0 minus f prime of 0. Okay, that is for the second derivative. Now we go to the next, minus 4. What is now the Laplace of the first derivative? So 4 times s f of s minus f of 0. And then plus 4 times the Laplace of y of t is our f of s is equal to 4 times what is the Laplace of e to the 2t? That is 1 over s minus 2. Okay? Then now we simplify. You have here s squared f of s. Given f of 0, this is your y of 0 is negative 1. So negative 1 times negative s. So you have here plus s minus f prime of 0. Your y prime of 0 is negative 4. So times the negative. So that would be plus 4 minus 4 s f of s. And then again, f of 0 is negative 1. So negative times negative is positive times the negative 4. So you have here minus 4. And then plus 4 f of s is equal to 4 over s minus 2. Then simplifying, you have here positive 4 and negative 4. So you now have here s squared f of s minus 4s f of s plus 4 times f of s is equal to 4 over s minus 2. So we can factor out your f of s here on the right and the left side of the equation. So that would be s squared minus 4s plus 4 times your f of s is equal to 4 over s minus 2. Therefore, finding your f of s is equal to 4 over s minus 2 times 1 over s squared minus 4s plus 4. What is s squared minus 4s plus 4? That is s minus 2 squared. So this is now therefore 4 over s minus 2 times s minus 2 squared is s minus 2 cubed. Sorry. Wait for a while. Para may nakulang tayo dito. This one. I forgot this S. Tama ba? Nawala yung S. So, ilagay natin dito sa kabila. So, this is meron pang minus S. Okay? Please ko muna, wait lang. We simplify first the right side of the equation. So, when you multiply by S minus 2, that would be 4 minus S times S minus 2. So, that would be minus S squared plus 2S. So, times natin yung 1 over S squared minus 4S plus 4. So, the numerator now is 4 minus S squared plus 2S. I forgot this S. Okay? So, this is now your f of S. And we are asked to find the solution for this, which should be a function of t. Then how can we solve that? Then we now apply the inverse Laplace transform. So we are to find the inverse of f of s, and we can evaluate that first by having the partial fraction. So let us have first the partial fraction. What is equivalent to 4 minus s squared plus 2s over s minus 2 cubed by partial fraction. So that is equal to a over s minus 2 plus b over s minus 2 square plus c times s minus 2 cubed. That is our solution by partial fraction. And then multiplying both sides by s minus 2 cubed, you will have your 4 minus s squared plus 2s is equal to a times s minus 2 square plus b times s minus 2 plus c. And then we try to equate coefficient of like powers. So let us expand first the right side. So you have here a times s squared minus 4s plus 4 plus b times s minus 2 plus c. And now we equate coefficient of like powers to find the values of a, b, and c. Let us start with s squared. Coefficient on the left is negative 1 is equal to, on the right, you have a. And then coefficient of s, you have on the left is 2. On the right is negative 4a plus b. Okay? But our a is negative 1. So negative 1 times negative 4 is positive 4. 2 minus 4 is negative 2. So therefore, b is equal to negative 2. And for the constant, you have 4 is equal to 4a minus 2b plus c. Therefore, from this, what is c? So 4 times negative 1 is negative 4. And then you have negative 2 times negative 2 is positive 4. So you have 8. Correct. Wait. So you have here 4 is equal to 4 times negative 1 minus 2 times negative 2 plus c. Sorry, 0 pala yun. So you have here c is equal to negative 4, positive 4, 0. So you have c to be equal to 4. And therefore now, we continue now with the inverse. So finding your f of t now. So finding the inverse of this. So the inverse Laplace of 4 minus s squared plus 2s over s minus 2 cubed would be equal now to the inverse Laplace of this. Our a is negative 1. So negative 1 over s minus 2 plus b. Your b is negative 2 over s minus 2 square. Sorry. Then plus 4 over s minus 2 cube. So we are now to find the inverse Laplace of these terms. Okay. So what is the inverse Laplace of negative 1 over s minus 2? What we have is what we have is 1 over s minus a. So we can factor out here negative 1. Okay, so this is equal to negative 1, the inverse Laplace of 1 over s minus 2. And then what about the next term? What is now the inverse of negative 2 over s minus 2 square? That would be, what theorem are we going to use? That is the first shifting theorem. That if the Laplace of f of t is equal to f of s, then the Laplace of e to the at f of t is equal to f of s minus a. So we are to shift s to s minus a. So we put it in a form of that would be negative 2 e to the 2t. The inverse Laplace of 1 over s squared. That is your first shifting theorem. We just shifted s to s minus 2, and that is equivalent to multiplication of e to the 2t. Okay, what about for this one? So this is plus 4, similar to this second term, the inverse Laplace of 1 over s cubed. And now we find the inverse of the following. So this would be now equal to negative. What is the inverse of 1 over s minus 2? That is simply e to the 2t. Minus 2 e to the 2t. What is now the inverse of 1 over s squared? So that is t. Okay, so that is minus 2 e to the 2t times t. But for this one, you have 1 over s cubed. So s cubed, it should be s to the n plus 1, but the numerator should be n factorial. So this should be 2. But we have here the multiplier of 4, so we can make this 2 times 2. So this is simply equivalent to 2, the inverse Laplace of 2 over s cubed. So that 2 over s cubed would be equal to, so plus 2 e, I forgot here the e to the 2t, e to the 2t by first shifting theorem. 2 e to the 2t, and then now the inverse Laplace of 2 over s cubed is t squared. Diba? F of s of t squared is 2 over s cubed. So you have here, this 2 over s cubed is your t squared. And you now have here, you can factor out your e to the 2t. So e to the 2t times t squared minus 2t minus 1. And that is the inverse of 4 minus s squared plus 2s over s minus 2 cubed, which is simply your f of t. Okay? So you now have the solution of that given differential equation. Again, we started with finding the Laplace of all the terms. And then since it involves derivative, so you have the transform of derivatives property of transform. You just apply them, then apply the given conditions, then you will end up with a function of s or your f of s. And then after that, you are to uh, find its inverse. But before going to inverse, you need to find the equivalent of 4 minus or the equivalent of 4 of f of s, which involves partial fractions. So you need to evaluate the values of the coefficient using partial fraction. And then after that, you find the inverse of each term. And the inverse is actually your function or the solution of that given differential equation.
Ma'am, excuse me po. Di ka po yun ay 2t squared yun sa final answer. Dahil po 2 e raised to 2t po kasi.
Which one?
Dun po
This
sa
one?
final answer. Opo, di ka po yun po last term sa ano eh. 2
Ah, yeah,
e
yeah.
raised
Sorry,
to
sorry.
2t
Yes, yes, yes.
minus t squared. Thank
Thank
you po.
you. Okay. So let us have another problem. Hmm. Example number 2, solve y double prime of x. This time I use a function of x, not a function of t, but it's just the same. It's a matter of the independent variable. So y double prime of x plus y of x is equal to 4 e to the x given at y of 0 equals 0 and y prime of 0 is equal to 0. Okay? So again, our solution is you take the Laplace of the given differential equation. So the Laplace of y double prime of x plus y of x is equal to 4e, or you can have it here, the Laplace of 4 e to the x. Okay? So what is the Laplace of the second derivative again? So you have s squared f of s plus s f of 0 minus f prime of 0 plus y of x, so that is your f of s, is equal to 4 the Laplace of e to the x. So substituting the given condition, S of 0 is 0 and f prime of 0 is also 0. Therefore, you now have your s squared f of s plus your f of s is equal to 4, and the Laplace of e to the x is 1 over s minus 1. So this is 4 over s minus 1. So here on the left side, you have f of s times s squared plus 1. Therefore, your f of s is equal to 4 over s minus 1 over s squared plus 1. And now you find the equivalent partial fraction. So this is a over s minus 1 plus, since you have here quadratic, so you have here bs plus c over s squared plus 1. And now we are to find the values of a, b, and c. We multiply both sides by this s minus 1 times s squared plus 1. So you have 4 is equal to a times s squared plus 1 plus bs plus c times s minus 1. So simplifying, you have here a s squared plus a plus bs squared minus bs plus cs minus c. And then equating coefficient of like powers, let us determine so the values of ABC. So for s squared, you have 0 is equal to a plus b. Coefficient of s, 0 is equal to negative b plus c. Okay? And then for the constant s to the 0, 4 is equal to a minus c. And then we have three equations, three unknowns. So we try to find the values of a, b, and c. Let us combine these two. So you have, when you add the 2, so you have 4 is equal to a minus b. And then we equate it with the first equation, 0 is equal to a plus b. Therefore, you have 4 is equal to 2a and a is equal to 2. Okay? So from, if a is equal to 2, then substituting it to the first, then b is negative 2. And substituting it to the second equation, negative b plus c is equal to 0. Therefore, c is negative 2 also. So therefore, what are now the uh, function f of s? So our f of s now is equal to a, this is 2, over s minus 1, plus bs plus c. So negative 2 and negative 2. So plus negative 2s minus 2 over s squared plus 1. And now we find the inverse Laplace. So the inverse Laplace of f of s is equal to the inverse Laplace of 2 over s minus 1 plus, again, we can have the linearity property, the inverse Laplace of negative 2s over s squared plus 1 plus the inverse Laplace of negative 2 over s squared plus 1. So you have here inverse of 1 over s minus 1. So that is 2, the inverse Laplace of 1 over s minus 1. And for this, minus 2, the inverse Laplace of s over s squared plus 1. Minus 2, the inverse Laplace of 1 over s squared plus 1. And now what are the inverse Laplace? For 1 over s minus 1 is, since a function of x, so e to the x. Okay, so this is 2 to the x. And then here, what is s over s squared plus 1? That is cosine of x. So you have here minus 2 cosine of x minus 2, 1 over s squared plus 1 is sine x. Minus 2 sine x. Or simply, our function f of x this time, since I use here a function of x. So the inverse Laplace, which is function of x, the function of x is equal to 2, you can factor out 2, e to the x minus cosine x minus sine x. And that is now the solution of our given differential equation.